Hello, it's me once again. We're Math Video. I hope this helps for your homework and stuff. And well, let's get started. Complex algebra. We're just reviewing the basic stuff, and for basic stuff, the basics of the basics. So we already talked about this in the classroom a little bit. Let me recapitulate. Um, if you, for example, take a real number x in the real numbers. What does this mean? Well, of course, it means that x belongs to the real numbers, which is that x is a real number. Okay, so you may think of the variable x as a little box with a number inside of it, and what we know about this number, well, we know it's a real number. So um, having a x in the real number is equivalent to think about x being as a part of the real line. Okay, so you know that the real line is from zero. It's here in the zero. Here we have the zero. It goes from minus infinity to plus infinity. So it's all the real numbers. So x in the real numbers is equivalent to choosing a point here in the real line. Okay, it goes the same with complex numbers. So if I tell you that I am taking c in the complex numbers, this is equivalent to take a point in the complex plane. So the complex plane is basically here you have the real line, the real line, and as I told you in class, here perpendicular to the real line, I have the imaginary axis. Okay, so it's the real axis and the imaginary axis. Here in the real line, you have the real numbers. You have 0 here, 1, 2, 3, up to infinity, and here all the negative, minus 1, minus 2, up to minus infinity. So it's minus infinity to infinity. And here in the imaginary numbers, you have the pure imaginary numbers. So here you have the imaginary unit, which is I, then you have 2i and stuff, okay? And here you have minus I, of course, minus 2i. So in the imaginary axis, you have all the pure imaginary numbers, and in the real line, you have the real numbers as usual. And that's the reason I told you imaginary numbers is actually not a very good name. Uh, in following this analogy, in a geometrical perspective, the real numbers can be thought as points over the real line, so they are one dimensional. The real line is one dimensional, and the imaginary numbers are. It's better to think about them like b-dimensional numbers. Okay, they are points over the complex plane. So it's better to think about it like b-dimensional numbers, because this name imaginary numbers makes people think weird things, like they are not real, they are imaginary, but in the usual sense of the words as we use them in our daily vocabulary. But it's not. This is mathematical vocabulary. They are mathematical terms. So real is just a name. Imaginary is just a name. So it's, if you want to think geometrically about this number, it's better to think about them like b-dimensional numbers. So and it's very common to use the letter C to denote complex numbers. So if I am telling you that I am taking variable c in the complex numbers, it's just a number over the complex plane. Okay, here it is. This notion is equivalent. So of course I have the sense, like in the coordinate plane, this can be think as the a coordinate, of the complex number. It's not exactly a coordinate, but you may think as it, out of it corresponds to a real number x, and this will be a pure imaginary part, right? Let's put I y. Okay, I think this is the rainbow. It's fine. It's cool. It's cool. Well, Um, so this is the number c, and as you can see, it's equal to the real part, which is x, and also it has the pure imaginary part, I y. So any number which is a complex number can be written in the form x plus I y. Okay, which is the famous and most common way we express complex number. You may think as they are the sum of a real number plus an imaginary number. Imaginary. Okay, so this is a complex number. It's you can think of them as that complex number. I mean, notice that, for example, notice that. Just let me check something real quick. Okay. Yes. Notice that, if, for example, let's think about 5. 5 is a real number, right? 5, it's a real number. But the reals, as you can see here, the reals are a subset of the complex numbers. This means that 5 is also an element of the complex numbers. And this is sounds a little bit weird, but if you express 5 as 5 plus 0i, which is the imaginary unit multiplied by 0, it's the same, right? Because 0 multiplied by I is 0, and um, the 5, well, it's still 5. So, and this works for every real number. So we notice that all real numbers are also complex numbers, right? It's not very common to call them complex numbers. I mean, sounds a little bit weird. It's uncommon, but they are. They are. I mean, they belong to the real numbers, which is a subset of the complex numbers. So technically, they also complex numbers. So what is very common is if you have a pure imaginary number, or for example 5i. This is of course an element of the complex numbers. Okay, 5i will be around here, let's say, but it's not in the real numbers. So 5i, of course, is not, never, never is a real number. Never, never, ever. So, what can I say? This is a pure imaginary number, let's say. Now, let's go to more interesting stuff. Basically, all pure imaginary numbers. I mean, if you have a number here over the imaginary axis, a pure imaginary number is always, for example, I, is always a real number multiplied by the imaginary unit. Okay, so a pure imaginary number is, this number is always real. Okay, it's always real, and it's multiplied by the imaginary unit, which of course is defined. Its squared is -1, as we previously mentioned in class. The imaginary unit has this amazing property. Is defined to be uh, that its square is -1. Okay, I want to mention this because there is people who say that the imaginary unit is the root of -1, but it's not exactly. It's plus minus, right? So the definition of the imaginary unit, sorry, is that its square is -1. So let's um, continue by saying that consider the complex numbers and consider the addition. Okay, well, this has the structure of a field. What do I mean? Remember the Do you remember the properties of real numbers that they, for example, if you take a real number and you add another real number, it is still a real number, so it's closed. it's basically the same. Okay, so if you take if you take a complex number and you add another complex number, the the addition is still a complex number. Okay, so and also if you take a complex number and you add zero, the result is still the same complex number. So it has an identity. It has an identity. And also, if you take a complex number and you may find its inverse, its additive inverse in this case, which is the negative. So complex numbers also have identity, which is zero, and they also have inverses, which are negatives in the same sense as real numbers. So this part is actually easy. And if you take the complex numbers and the product, it happens the same. Okay, if you take one complex number and you multiply by another complex number, the result by multiplying two complex numbers is still a complex number, so they are closed. If you take a complex number and you multiply by one, you get the same complex number, so the identity is one. And if you take a complex number and you are able to find another number always for every complex number, uh, which its product is the identity. So yes, we have inverses in the case of complex numbers, so they have the structure of a field, and they also are commutative. They also are commutative. Um, in remember, commutative is you can switch the order just like that, and they also are commutative. Okay, associative. Sorry, they also are associative. The only thing that you lost when going from the imaginary to the real numbers, I mean, of course, the dimension, for example, here the dimension is 1, you're jumping to a dimension 2 space, but it's also the order. Notice that, for example, here in the real numbers, I have order. I have 0, then 1, then 2, then 3, so I have order, okay? But how do you order numbers in a plane? I mean, it's first this, then this, then this, or then this, or then this one, or then this one. Then which is the first one? Which is the second one? I mean, maybe you can came up with an idea of how to order points over a plane, but if you give me an idea of how to order them, how to put them in an order. In order, I can give you another idea. Actually, there is plenty ways to establish an order over a plane. It's not unique, and there is no natural way to order them like in the real line. In the real line, it's pretty much natural how to order them. So basically, the conclusion is that a complex number are not ordered. Okay, you cannot say, and this is for real, guys. You cannot say that, for example, I is greater, or 2i is greater than I. It's greater. No, this is not a thing in the complex number. They are not ordered. Okay, so 2i being greater than I, it doesn't make sense. In the complex number, we have no order. Okay, we have order. For example, 2 greater than 1. Yes, we have order in the reals, but we have no order in the complex numbers. Okay, it's it's just a fact. What else? In, in one of the things here, you may think, well, but zero is a real number, so is really the zero the identity of the complex number because it's a real number? Well, as I mentioned before, yes, zero and one are both real numbers, but it's easy to write them as complex numbers. Zero is just zero plus I zero, and one is just one plus I zero. So they are complex numbers as well. So it's fine. It's fine. They are the same They have the same identity and the same inverses. I mean, in the case of the real numbers. Okay. So let's jump to the next thing. Yes. This is also a recapitulation, you may think, because if you take a real number C1 and another real number C2, and they are complex numbers, of course. So if they are complex numbers, you always can write them as in the form x plus iy, right? In this case, I'm going to write x1 plus iy1, and c2 will be, of course, x2 plus iy2. So these are it's also called the rectangular form of the complex number. Okay, it's x plus iy, a real plus a pure imaginary. If I take the multiplication c1 and multiply by c2, of course, I substitute c1 is x1 plus y1 multiplied by c, sorry, here is c2. c2 is just x2 plus iy2, and well, you may skip this calculation, it's very quick. I mean, this is real and this is real. Okay, remember that x and y are real numbers. X and y, I'm not gonna put this sub index, but they are real numbers, and in order to compute this product, you only have to respect that the square of I is -1. Okay, this amazing property. So you can, I mean, you may proceed as any calculation in the real numbers, doing the way we multiply in the real numbers. Just respect that I square is -1. So you have x1 plus x1 by x2, x1 x1 by y2. I'm gonna put y2 and then the I, plus x2 y1 I. I'm doing this multiplication, and finally I squared y1 y2, because it's y multiplied by y, it's I squared. I multiplied by I, yes. Finally, this is a real number, this is a pure imaginary, and this I squared is -1, so actually this is a real number. So it's x1, x2, I squared is -1, so it's minus y1, y2. You can put this in parentheses, so we have the real part here, plus, and this is I, and this have I, so I can take out the I, as I can factor out the I, so it's what is inside. Now that I have factored out the imaginary unit, what is left inside, it's x1 and y2 plus x2 y1, x2 y, x2 y1. There it is. So as you can see, we always get, let me put it in another color, this will be the real part, x plus imaginary unit y. So I have the x plus iy form of the complex number. Okay, so whenever you have products of complex numbers, even if it's more than two complex numbers being multiplied, you can recover the x plus iy form of real numbers. Okay, so let's do another thing. For example, if I take, well, let's do an example first. Let's do an example, a quick example. Let's imagine C1 is, I don't know, let me think. I have my notes here. 1/2 plus 2i multiply by -2 plus I. So I just perform the multiplications, right, like this. So 1/2 multiplied by -2 is just -1, right? -1. 1/2 multiplied by the I, the imaginary unit, is 1/2 multiplied by the imaginary unit, just like that. And here 2i by -2, it's -4i. 2i by I is plus I squared 2, right? So doing the calculation, I squared is -1, so it's -1 -2 plus I factor out the I I, what is left inside, 1 over 2 minus 4, okay? So this is minus 1 minus 2 is minus 3 plus, and I have to perform this calculation, can do it like this. It will be minus, it's I multiplied by minus 7 over 2, right? So this is minus 3 minus 7 over 2i. And this is the real number, this is the pure imaginary, so this is the x plus iy form of the real number. X will be minus 3 and y will be minus 7 over 2. Okay? Pretty nice, pretty nice, pretty nice. Now, another thing we can do, for example, if I have an C complex number, okay, this means it can be written as x plus iy, okay? What if I want to take the square of this complex number? Well, remember, the square is just the multiplication by itself, right? 2 times in this case. So it's x plus iy multiplied by itself, x plus iy. I mean, because c is equal to this, I'm just making a substitution. Now, I mean, it's like taking the square of this, x plus iy. It's a binomial square, right? So you can apply the formula. Just remember that I squared is minus 1. Now, it's the square of the first, double the product, plus 2 x, y, and the I, remember, here is the I, x by this, double, and the square of the second, which is I squared, y squared. And now let's do the computation, x squared, I squared is minus 1, so we have a minus y squared, and 2i x and y, okay? So this will be the real part, this is the x, let's say, and here is the I, and the 2xy will be the imaginary part, okay? The imaginary, pure imaginary part. So we recover the x plus iy form of a complex number. So it's something you can always do, okay? So if, to name an example, for example, if the number is c I minus 1 squared, just take the square, right? Just take the square and that's it. That will be it. Square of the first, double the product, square of the second. Do the calculations. Apparently these cancels each other, so it will be like this. That's the x plus iy form, okay? You have to write it like this, because if you write it like this, you're not writing the x part, okay? And in the exercise, I am requiring the x plus y iy form, okay? So you have to rewrite it like this. Now, another example which is funny and useful for your homework. Another example, for example, if c is equal to 1 over I, over the imaginary unit, how did you express this in the x plus iy form? Well, let's agree that 1 over I, if I multiply it by I over I, is the same, right? Because I divided by I is 1. It's basically it is 1, okay? So it's a division. I divided by I is 1, so I am multiplying by the unit, which leaves the number the same. So I can do the multiplication of fractions. So it's 1 multiplied by I is just I. 1 multiplied by I is I squared. And I squared is minus 1. and I divided by minus 1 is of course minus I. So we conclude that 1 over I is equal to minus I, which of course is 0 minus I. And that's the x plus IY form. Okay, so we recover it. Another useful example could be 1 over, let me see, 2 plus I. So you may be, I mean, let's say this is our imaginary number. You maybe are tempted to proceed like this. Like, I'm gonna do the same as above. I'm just gonna, I'm just going to multiply above and below by the same, right? But if you do this, I mean, 1 multiplied by 2 plus I is 2 plus I. And below I have a square. The thing is that if you do this, you don't get rid of the imaginary unit below, as you can anticipate. I mean, it's square of the first, double the product, square of the second. So you have 2 plus I. This is a minus 1, so it's 4 minus 1 is 3 plus 2i. You didn't get rid of the complex number below. I mean, in the denominator. So what do we gotta do? Well, 1 over 2 plus I. Instead of multiplying by the same, I'm gonna multiply by the same, but with the sign change. Okay, so I'm gonna change the sign, a plus for a minus. If I had a minus here, then I will change to a plus. So the trick is to change the sign. And of course, we're doing a multiplication. This division is still 1. 2 minus I over 2 minus 1 is a 1. So we perform the multiplication fraction is 1 multiplied by 2 minus I, it's 2 minus I. And here I have binomial conjugates, right? Can you notice? Did you recognize them? They are binomial conjugates. So it's 2 minus I, and here, how do you take the power of, well, not the power, the product of binomial conjugates. It's the square of the first, which is a 4, and minus the square of the second, okay, which is the I squared. And squaring the I will give me a minus 1. So it's 2 minus I over 4 plus 1, right? Because the I squared is minus 1. With this minus, you get a plus 1. So it's basically 2 minus I over 5. And you can distribute this 5. So it's 2 over 5 minus 1 over 5I. And that will be the x plus IY form, okay? In this case, the x is 2 over 5, and the y is minus 1 over 5. That will be the I, okay? So, this is a good example that actually gives us a hint that this quantity with the sign changed is actually very useful, so we are going to define it. If C is a complex number, sorry, if C is a complex number, it means C can be written as IX plus IY, and we are going to define its conjugate with a little bar over the C. We are going to define it as the same X but with the sign changed, minus IY. Okay, so the conjugate of a complex number is just the same X plus IY form with the sign change. Okay. Um, for example, if C is equal to, I don't know, 2 plus 3I, the conjugate of this complex number is, of course, 2 minus 3I. And if the number is C equal to 4 minus 5I, then the conjugate of this complex number is, of course, 4 plus 5i. So that's what it is. Now, a final thing I want to mention before ending this video, because I think it's maybe getting a little bit longer than I thought. Is notice the following. Oh, I discovered how to. Well, it's nice. Um, if as I told you before, c is a complex number, right? So it's equivalent to think of c as an element of the complex plane, right? So you have the real axis here, and you have the imaginary axis here, okay? And by choosing a point over the complex plane, of course you have the real part, and you have the pure imaginary part, okay? So it's pretty much similar to R2, right? To the coordinate plane, because it's actually isomorphic, which is a very fancy word mathematicians use to tell that two mathematical objects are basically the same. It's isomorphic, yes. Um, in this case, the complex plane, geometrically thinking, it's pretty much the same as the coordinate plane. Okay, algebraically thinking, they are not the same. They are not near to be the same. But geometrically, uh, it's basically the same thing. So you can think of a complex number as the real part plus the pure imaginary part, but you may also think of them as, sorry, I'm gonna take another color. You may think about them like a vector. Remember that from physics? A vector. So it's an arrow and an angle. So the arrow, you will take the length of the arrow, which is r, and the angle of the arrow, which is theta. Okay? So you may have a complex number, you may have this triangle, basically. And of course, you can apply trigonometry. Trigonometry will be the imaginary part. And you may have a complex number in the x plus iy, which now you know why it's also called the rectangular form of the complex numbers. But you also may have, like in physics, the polar form, okay, which is the length of the arrow and the angle of this arrow. Okay, this is the polar form. Now, um, how can we express this in a better way, which is equivalent to the rectangular form? Just remember that r is, of course, x squared plus y squared, and this has a name. This is called the modulus. Oh, I'm just remember. This class is in Spanish, right? I okay. I just remember this class in Spanish. Well, sorry, we're gonna continue in English. It will be weird to change right now. Um, modulus, which in Spanish is el módulo, sí, el módulo of the complex number, and um, we also have the angle, which here we call the argument of the complex number, which aka the angle. Okay, in Spanish it's the same. It's the el argumento. Okay, el argumento. What else? All right. Which of course, from trigonometry, you know that the tangent of theta is y over x. So basically, the angle or the argument is the inverse of the tangent of y over x. Okay, so um, as well from trigonometry, you know that, for example, the sine. Just let me see if you are seeing this. Yes, you are seeing the sine. I'm gonna do this just in case. The sine of theta is equal to y over r, right? And the cosine of theta, following trigonometry, functions, it's x over r. I mean, this is not a surprise. And from this, we conclude that x is equal to r cosine of theta, and y is equal to r sine of theta. So if we write the complex number in the x plus iy form and we substitute the polar form, we end up with r x, remember, is r cosine of theta plus I, and y is r sine of theta, right? So if we have an r here, we can factor out the r. Okay, let's do it. So we have r multiplied by the cosine of theta plus I sine of theta. And there is a thing that maybe I can explain in detail in the classroom, or if you may ask in the comments as well. I mean, this quantity cosine of theta plus I sine of theta, this expression, um, we know from, I mean, from details that I'm gonna omit, that you can of course ask me, but it will be not suitable for this video. That the exponential to the I of theta is actually equal to cosine of theta plus I sine of theta. So this exponential has this expression, this exact same expression. So we can rewrite as r multiplied by a I to the I theta. Okay, and this is the famous polar form of complex numbers. Okay, the polar form is c equal to r e to I theta. Okay, this is the famous polar form of complex numbers. And it's what is asked to do in one of the exercises of the homework. Okay, you are required to find the argument, to find the modulus, and then write the polar form. Okay, so a quick example will be, let's do a quick final example. If the number is, for example, 1 plus I, then the modulus will be x squared plus y squared, right? So in this case, x equals 1 and y equals 1, right? So we substitute 1 squared plus 1 squared root. It's 1 squared is 1, 1 squared is 1, 2 root of 2. That's the r, okay? That's the modulus, root of 2. And by the way, the modulus is always a real number. And for example, the argument will be the inverse tangent of y over x, right? But in this case is the inverse tangent of 1 over 1, which is 1, the inverse tangent of 1, which is in sexagesimal 45 degrees, right? In radians it will be p over 4, right? Radians. Let's use the sexagesimal value. So it's more common to use the radian, right? I mean, you can use the sexagesimal value, it's fine, but it's more common to use the radian number, okay? So yes, let's better use this one. It's the more common one. So we already have the angle, which is pi over 4 in radians. So we have r, we have theta, and the polar form is r e to the I theta, which in this case is root of 2 e I p over 4. That will be the polar form, okay? Which is equivalent, this is equivalent to 1 plus I. It's the same point in the complex plane. So it's just a different representation, which turns to be very, very useful for a lot of applications. And well, I hope this video is not too long, and hope it helps for your homework. I'm planning doing another video, but I will like to have the next classes, and then uh, I can do another in case we don't have enough time and stuff. Okay, so well, see you, boys and girls.